We're going to talk about inverse functions, and I have two functions listed for you, f of x and g of x, and we're just going to define each of these functions by these four data points. If you'll notice, for f of x, when x is 0, f of x is negative 1, 1 for x equal to 1, f of x is negative 2, and so forth. If you'll look at g of x, the domain and the range are exactly flip-flopped for f of x and g of x. That would make f of x and g of x inverses of each other. Now, inverse functions just mean that the domain and the range are exactly flip-flopped of each other. Not all functions have inverses. We'll talk about that a little bit later. But for these two functions, they are inverses of each other, and we would say that g of x is equal to the inverse of f of x. That's what this little -1 superscripted on the f means. It just means that it's the inverse function of f. To find the inverse of a function algebraically, we're going to follow a three-step process. Here's our function, f of x equals 3x plus 1. Step number 1, in finding an inverse, says to write it as y equals. So let's do that. Y equals 3x plus 1. Next, we're going to swap our x's and y's. So wherever there's an x, I'm going to put a y. Wherever there's a y, I'm going to put an x. So I'm going to have x equals 3y plus 1. Next, I'm going to solve for y. That's my third step in the process. So I'll get x minus 1 equals 3y. And then y equals x minus 1 over 3. Cleaning this up just a little bit, just to make it look like an inverse. All right, the inverse of f is x minus 1 divided by 3. Now let's look at another function. Follow our same three-step process. We'll do one that looks a little bit uglier, but really isn't so bad. I'm going to write it as y equals. So y equals the cubed root of x plus 4. Then I'm going to swap my x's and y's. X equals the cubed root of y plus 4. I'm going to subtract 4 from both sides. Cubed root of y. Then I'm going to cube both sides, and y is going to equal x minus 4 quantity cubed. And then cleaning it up once again, the inverse is x minus 4 quantity cubed. Now basically what this does is it swaps the domain and the range, and the x's and y's, their x values and y values are swapped for the f and his inverse. When graphing inverse functions, I've graphed our 3x plus 1 on this blue line, and I've graphed our inverse function, x minus 1 over 3, on this red line. You will notice that they are reflections about this y equal x line right down through here. That's because their x and y values are flip-flopped. And whatever was x before is now y, whatever is y is x. And so your inverse functions will always be reflections about this y equal x line. So we'll look at our other function that we found the algebraic inverse of, and we'll look at those two graphs and see how they flip-flop. Beautiful picture once again. We can see our original function, our f of x, is the cube root of x plus 4. And our inverse function that we calculated algebraically, x minus 4 quantity cubed, is a flip-flop along this y equal x line. See how the two flip-flop along that particular y equal x line. You'll be able to see that when you graph the two functions. If you were using your calculator, you would graph one of the functions in y1 and the other one in y2, and you could see that flip-flop across that y equal x line. Now, I said that not all functions have inverses, and that's because functions are not necessarily one-to-one. This is the graph of x squared, just a simple little function, x squared. It does not have an inverse entirely along its domain, because in order to flip-flop it across this y equal x line, it would have to be something that looked like this, and that would not be a function because it would not pass a vertical line test. So when you flip-flop a function that doesn't pass what we call a horizontal line test, it is not one-to-one. And that's what that refers to, one-to-one. It's not a one-to-one function because it does not pass a horizontal line test. In essence, when you flipped it and made an inverse of it, it wouldn't pass a vertical line test, meaning that it wouldn't be a function. Here's another function that is not one-to-one. If you'll notice, if I were to see if it passed a horizontal line test, I would find that it hit in more than one spot, so it wouldn't pass a horizontal line test. Therefore, this particular function does not have an inverse. And that's the graphical test to see if a function has an inverse. And this one would not. Just another normal function, the absolute value of x. He does not have an inverse because he does not pass a horizontal line test. In order to give him an inverse, what we could do is we could say, well, he has an inverse as long as we only consider this right side of the graph. And as long as I only consider the domain from 0 to infinity, he would have an inverse. In some cases, we'll do that, especially with x squared and absolute value functions such as that. In order to verify that two functions are inverses of each other, we have our f of x is 3x plus 1, and our function inverse that we found, x minus 1 all over 3. We need to show the following, and we need to show it for both cases. We need to show that the composition of f and his inverse equals x, and we need to show that the inverse of f is also x. So I will do the first one. F of his inverse of x. So our main function looks like f, 3 times x plus 1. I'm going to substitute in the inverse, which would be x minus 1 over 3. And then I'm going to show that this equals x. So I'd multiply, my 3's would cancel, I would get x minus 1 plus 1, and then I'd get that this equaled x. I'm also going to do this for the other case. Let's see if I can squeeze that in over in this area over here. I'm going to do f of the inverse of f of x and see what that equals. I've got the inverse, which is x minus 1 all over 3. And I'm going to see, let me make sure that we separate this thing out here. I'm going to see that this equals x. So in place of x, I'm going to write my f. Oops, I need my other parenthesis here. I'm going to replace my f, which is 3x plus 1. I'm going to do the manipulation here, and I'm going to get 3x over 3, because a plus 1 minus 1, the 1's go away, and then this also equals x. I've now verified that these two functions are inverses of each other.